Now I want to go to another topic. In the 80s, when we had no Ethernet boards here, except one of my friends who will talk, there was it was an internet in the United States called NSFNet, developed by Van Cerf, and it was with IBM computers running a strange operating system called BSD. Because this started sometimes in 1983, it was the first TCP/IP stack and the first operating system who worked on the large scale was compared to that time on the internet. So it was the big push to develop the internet, and we have now the chance to have here with us Mike Karels, who took the place of Bill Joy in the California Computer Development Group at Berkeley, and he was the chief of this project, the head of this project for years. BSD, BSDI, and FreeBSD. Mike?
Good afternoon. Unlike the other people in this session, I'm talking about something fairly long ago. In fact, about 40 years ago. So the topic is BSD's role in the early internet. So first of all, what is BSD? BSD stands for Berkeley Software Distribution. It's a series of software releases that were distributed by the University of California at Berkeley. The releases started unnumbered. It wasn't planned to be a series. There was the Pascal tape. There were various other add-ons for Unix, like the C shell and VI. And that gradually grew into something a little bit different, which was eventually called the Second Berkeley Software Distribution, or 2BSD. Thank you. 2BSD started again as PDP-11 add-ons. So this was version 6 Unix on a 16-bit mini computer. And it started out with the add-ons, but eventually it went to full systems. So it had modified terminal driver, for example, various other things in it. And I'll talk very briefly about one of those in a minute. About that time, the VAX came out, a 32-bit mini computer, and it supported virtual memory, unlike the PDP-11. So Unix got ported to that by Bell Labs, but it didn't support virtual memory, so Berkeley did that, and that came out as 3BSD, and then other things came out as 4BSD, 4.1 BSD, et cetera. So these were developed and supported by the CSRG, the Computer Systems Research Group, at the University of California. And so the systems became known as Berkeley Unix. So I'm going to talk a little bit more detail about 4.2 BSD, which came out in September of 1983, so just about 40 years ago. It had the first widely available TCP/IP implementation in it. It wasn't the first TCP implementation, but it was first widely available. It was done on a version done at BBN under contract to DARPA, which was the Defense Advanced Research Projects Agency, if I recall correctly. And that was a contractor in the government that contracted for advanced research. It was then integrated and enhanced by Berkeley to the point that when Berkeley got the final version from BBN, Berkeley said, no thanks, we like our version better. It also included the socket interface to networking, which was designed to be a protocol agnostic interface. So when you constructed an address to hand to a TCP socket, you didn't just give it an internet address, you gave it a sockadder structure, which has an address type, internet, and it has a 32-bit, happens to have a 32-bit IP address, 16-bit port number. It also included user-level networking support, support routines like, say, get host by name, which would translate from a host name into a network address. And that was done at that time by just a table lookup. There was a big text file and later a hashed text file, but it had complete addressing for the internet. such as it was. It came with a number of utilities, some of them, a number of networking utilities. Some of them were the so-called R commands, rlogin, rsh, rcmd, rcp, and it also included the standard protocols like telnet and ftp. Ran on a VAX again, and like the other releases up to this point, it required a Unix source code license. That really didn't matter too much because the target audience already ran Unix, which for these systems required a Unix license. That became more of a factor later. So a little bit about my involvement with BSD, how I fit into this picture. I started out as a graduate student in molecular biology, took a left turn at some point, started hacking on things on the PDP-11 in the lab, ended up being one of the authors of 2.9 BSD, which was a complete 16-bit PDP-11 Unix system. And then I went from there to being the principal programmer at CSRG, which was a big promotion. And that was in July of '83. And you'll remember that 4.2 came out in September of that year. Obviously 4.2 was mostly done when I started. Bill Joy and Sam Leffler were the two people who had done most of the work, including the design and refining the TCP/IP engine, doing the socket interface, et cetera. So suddenly I was the developer and maintainer of the most common TCP/IP implementation on the internet. So talking about BSD and internet development, 4.2 had a test release called 4.1c, but it wasn't very widely distributed. It was used in universities that tested this. 4.2 was much more widely used at universities and also research organizations. Was used on the ARPANET, which is the ARPA research network funded by DoD in the US. Later the MILNET, when that was split off from the ARPANET. Was also used on local ether networks because Unix didn't previously have much in the way of networking. And then of course there are some things that routed between the two, so it was a true internet at that time. 4.2 was also the basis for various commercial systems. Sun Microsystems, as mentioned earlier, Digital Ultrix were derivatives of 4.2 BSD, and various parts of 4.2 were used in other commercial versions. Now at this time, this was the first release to support TCP/IP on a wide-scale network on Unix. And so, needless to say, there were a few bugs. And it didn't have very sophisticated algorithms. It had the algorithms that you needed to open, close a connection, et cetera. But it didn't have things to deal with some of the problems that started creeping up. So it needed bug fixes and it needed new and additional algorithms. So I'll talk about the Nagel algorithm. This was the first algorithm I added to 4.2 other than bug fixes and things like that. There was this guy, John Nagel, who had a rather tortuous path to the internet. It'll sound sort of familiar. He had a 4800 baud connection, which in turn, that went halfway across the US, went to a 9600 baud connection the second half of the way across the US, and then connected to MILNET. And so, needless to say, there were problems with this path. And John looked at the path and what was TCP doing, and there were a lot of cases where there were multiple packets for the same connection in the same queue. And so he had a nice self-tuning algorithm to gather up packets during one round-trip time. And if the connection was fast, like a local area network, you type a key, you'd get an echo, connection was idle again, no more delay. But on a slow link like the ARPANET, it would delay things up through a round-trip time. So I looked at implementing this, and I found the right place in TCP output. And there was a 3-line test that was somewhat complicated, and I looked at it. I thought, if I just delete the middle line out of those 3, then I'll have the Nagel algorithm. So I deleted that line, and I tested it, and sure enough, it was the Nagel algorithm. And so needless to say, I went looking for another line of code to delete, make things better, but second one wasn't quite so easy. So a couple of years later, this is formatted differently in PowerPoint, but I think you can read it. A couple of years later, the ARPANET was becoming heavily overloaded with the number of systems that were becoming attached to it, and it was the main long-haul network for the US. So it used 56K links, which were not bad when it was first started, but it was getting to be a bit slow. It used packet switching on mini computers called IMPs, or interface message processors. Round trip times were getting to be fairly long, up to about 45 seconds or even more. So typical connections would retransmit frequently. And it turned out most people would just say, well, again, there's not enough bandwidth. What can we do? But this guy named Van Jacobson worked up the hill from me at Lawrence Berkeley Lab, looked at it, and like John Nagel, he saw there were a lot of retransmissions. And so he looked at the code and he looked at the behavior, and the two didn't match up. The code said, just send when the window allows it. But the behavior would send out batches of packets, say like 8 packets at a time, and that would be a window of packets, and that would overflow the queue at the next hop router to the bandwidth limited network. So he called that blast and lose, where you'd send a window of packets. Some of them would get dropped, you'd stop, retransmit, fill in a hole or two, and then send another whole window of packets to catch up, and of course it would happen all over again. So Van invented an algorithm which had a cute name called slow start. And obviously what you want to do is, instead of starting out very quickly, you want to start out slowly. So it would open the window by 1 packet per packet, which is an exponential opening. You start out the connection with just 1 packet, the SYN, and then when you got back the ACK for that, then you're allowed to send 2 packets. When you get back the ACK to the second of those, you can send 2 and 3, and then the next packet you can send 4 and 5, et cetera. So this was a good algorithm to try to tune the hosts to the network. This was good to a point, but if your window is still too large, you would still overrun the network. And the reason for that is that if your total window would overflow the buffers on the routers, then you would still have problems. So there was a congestion avoidance algorithm that Van invented, went along with slow start. So once you got to about where the last drop packet happened, a window of a certain size, then you would start opening the window linearly, probe for additional bandwidth, but not open it quite so quickly. So this went fairly quickly from being an experimental algorithm that was being tested at Berkeley to something that Berkeley's test sites, various universities got updates from us periodically, and they used it, and it helped a lot, and it made things better for the hosts that were using it. So it actually went from an experimental algorithm to a required algorithm in just a couple of years. It was published in SIGCOMM 88, if you want to look at it more. Later, there was an algorithm added called fast retransmit, which recovers from lost packets more quickly. If you had a couple of lost packets in a window, you'd stop, retransmit the first one, retransmit the second one, eventually get started, but you lost several round-trip times worth of data sending ability. And fast transmit, you lose less than 1 round-trip time. So it seems like it works faster than the speed of light, but it doesn't. So there are other BSD influences on the internet. One of them is involved with the domain name system. So I mentioned that there was this big flat table of internet addresses, hosts and internet addresses, and that obviously didn't scale very well. As a matter of fact, at its peak, I believe there were 6 people maintaining that table full time. So Paul Makapetris, not at Berkeley, designed the domain name system, or DNS, and he did the first implementation on TOPS 20. Second implementation that I know of was done at Berkeley by a group of grad students originally. And they called it BIND for Berkeley Internet Name Domain System. And it was integrated into BSD. The server called named was one of the standard services. The C library resolver replaced getHost by name, so old programs would still work. And this was probably the most widely used DNS implementation for quite a few years. And so that had quite a bit of influence on how things got done, including how hostname lookup got done on BSD-like system or Unix-like systems. Berkeley also influenced internet standards. There was a group called the Internet Engineering Task Force, IETF. Host requirements RFCs were done there. And I spent a lot of time at committee meetings there. Eventually there were a couple of RFCs, RFC 1122, RFC 1123, which are Internet Host Requirements RFCs. And so Berkeley had a fair amount of influence on that. I mentioned also the socket interface. There was a group called POSIX that was doing Unix APIs, which is where I met Jeff, actually. But they decided to standardize network standards, decided to standardize 2 standards, including the socket standard. So I had a lot of input into that. So that was another big influence of Berkeley. I want to talk a little bit about BSD and open source. All of the things I've talked about so far were in 4.2 and 4.3 BSD, licensed Unix systems. We had to have a Unix source code license. Now, CSRG received a number of requests for partial releases, just the TCP code, just the telnet code, whatever. But we had no mechanism for doing partial releases, no way of delivering it, no way of licensing it. And in fact, we hadn't verified that any particular part didn't have Unix source code in it. So there was a new release called Net1 that we put together. We reviewed the code. It was a vertical slice through the system. It had user-level code, clients and servers. It had library code. It had kernel code, the TCP/IP protocol implementations, the socket layer, and this was made available with the new BSD license and a new BSD copyright, which says you can basically do with what you want with it as long as you give us credit and don't sue us. And then there was a version called Net2, which included a nearly complete system, had a few missing kernel files, but there was a little lawsuit that intervened. And after that, there were new releases from Berkeley. 4.4 BSD Lite was the first release after the lawsuit. And that included everything that was in Net2, some minor exceptions, and was open source, was Berkeley licensed. I'm going to do this one very quickly. There was a company called BSDI that was developed a version of Net2, which was a complete system and sold it commercially. Unfortunately, when they advertised it, they used the phone number spelled out as 1-800-ITS-UNIX, which may have been the trigger for the lawsuit in question. In any case, that was filed by USL, which held the Unix trademark and patents, against BSDI, and then later against UC Berkeley as well. So the lawsuit was settled. BSDI first release 1.0 came out. There had been a number of test releases sold before that. And this was used in a number of commercial firewalls, routers, was used in websites later. And believe it or not, I believe BSDI was the first commercial site on the World Wide Web. I can't verify that. I guess I'll say a few words. It was founded by some BSD developers, people related to Berkeley, including me. And so it was kind of people who already knew this code who developed the new system. One other thing I wanted to mention is that although the BSD sort releases from Berkeley ended a while back with 4.4 Lite, there are a number of BSD systems ongoing. There are the main three, which are FreeBSD, NetBSD, and OpenBSD. which started based on Net2 and or 4.4 Lite 2, or split off from the others. There's one called Dragonfly BSD. There's another one called Darwin, which may be less known. But Darwin was done by Apple, and it was the base for Mac OS. It was open sourced. I'm sure by now Mac OS has diverged tremendously from the original BSD code. That was another influence of BSD on the network. So at this point, I'll take any questions. Yes?
Yeah, I'm wondering...
Oh, wait for the microphone.
Thank you very much. Sorry. Yes, okay. I'm wondering, you mentioned some legal lawsuits, but didn't talk about this. You had everything to succeed. I mean, I look at the code, I'm a BSD user, one of the last ones, instead of Linux. But I'm feeling like I'm becoming lonely, because even through NAS, as an example, switched from free BSD to Linux lately. How was the influence of this lawsuit in the development of BSD? Because you didn't mention this.
That's hard to know.
Why did you lose this war? Because the code is brilliant compared to Linux. Linux is a mess. It's still a mess. Even Linus Torvald recognized this as a kernel founder. Instead, BSD is done by engineers, and I don't get it. I mean, it's an anomaly why you lose the market shares. And now in BSD, I cannot, it's not my main system, it's an Apple one based on BSD, but in drivers, for instance, you don't have companies involved in developing the drivers. This is why Linux is gaining momentum. Thank you very much.
Well, Linux has more market share. There's no doubt about that. There are a lot of BSD users. I'm part of the FreeBSD community, and it's very active. There are fewer drivers for FreeBSD, but we've been fairly successful in getting companies to dual license their drivers, do a BSD licensed version as well as a GPL version. There are people, including myself, that think BSD is more structured. Maybe it's the engineering background that you mentioned. I'm not sure. I myself was trained in molecular biology, so that didn't help much directly. But I think it's a matter of opinion. Some people think BSD is a cleaner system, more maintainable. So, but it is really a matter of personal taste at this point. Is there another question?
How do you think, Mike, being trained as a biologist instead of being trained as an engineer has affected the way that you do software?
I'm not sure how to answer that, to tell you the truth. I'll have to think about that. Any other questions? If not, we're probably getting close to our time limit. So. Okay, thank you.
Thank you.